All right, how you guys doing today? Reasonably all right. Let's see. Where's Santiago? He's missing. Do you guys know if Santiago is going to show up?
Probably. Oh, yeah, he was. He's probably just fine.
Okay. Cool. That, I mean, I think that's everybody but him and Nikhil. Neat.
Yeah, he's on his way.
Great. So today we're going to go over the homework and review for the midterm. So I'm not going to present anything new today. And we're just going to go over the homework. So I haven't actually looked at it. Did everybody get it done? More or less? Okay. No?
I ran out of time.
Okay. Did you get something done?
Yeah.
Did you turn something in?
Yeah.
Sweet. Something is better than nothing. Yeah, so as of the last time I looked, which doesn't include this one, everybody had every homework in when I graded, which is great. That's often not the case. There's often somebody who's missing something. So everybody's doing good so far. So today we're going to go over this homework. Hello. So today we're going over this homework. Some of them I'm not gonna go through all of the math of all of the homeworks because that would kind of take forever, and then we wouldn't have any time left for review. But I want to make sure that I at least touch on each one of these problems and what I wanted you to get out of it. So this first problem. Random walk processes are governed by a diffusion equation, a diffusive process like this. So the first question is, show that this is a solution to the diffusion equation. Did anybody have any troubles with doing that? It's relatively painless. You just have to take this and drop it into the time derivative, which you got to do a product rule because you got a time here and a time here. And then this one brings down an x squared and a 40t, and this one you get another 40. You get another root 40t. Another root 4 pi d. And then on the right-hand side, you take the space derivative, which doesn't have the product rule, but brings down what's in here, and then everything cancels out. Mostly, this is an exercise in putting your hands on this. So seeing that Gaussians that evolve in time in this fashion, x squared over t, and you can see from this that x squared is going to go like t, like x squared. Whenever you have x, it's going to be off by a square root. Was that?
Did that the wrong way.
Which way?
I solved the PDE for the Gaussian. Whoa. It was a pain in the ass.
Well, that is a better way to do it. I mean, anybody who did it that way is somewhat stronger.
There was a substitution like in the integral that you have to make that I didn't end up like finding. I had to like find online. I was like, oh, you have to do this. It'll look like this. I'm like, you know what? I'm just gonna. It's about this integral, so I did that. So I might have skipped page stuff, but like.
Okay.
That's a lot simpler than what I did.
Yeah. I mean, if all I'm saying is show that this is a solution to this, all you have to do is plug it. Not necessarily derive this as an equation or solve this. So, but you know, however you get there. So if you actually solve the equation, that's super useful. And I don't have a solution of that worked out, but I can track one down if you really want to see it. I have that solution somewhere. I can pull it up for you.
I think I'm going to stick with the easier method.
Yeah. Okay, second bit, show that the mean squared of the position of the material increases linearly with time. So specifically, this x squared times n, integrate that, goes like 2 dt. So this is relatively painless. You just got to write down x squared n dx, which is then going to be x squared, so average x squared equals e to the equals 1 over 4 pi dt, square root of that business, e to the minus x squared over 4 dt. So how do you do this integral? Was that?
Integration by parts,
Okay, you can integrate by parts.
and then the error function.
You don't need an error function because this goes over all space. So it's easier. So you can integrate from minus infinity to plus infinity. So you don't need an error function. You can just use the Gaussian integral. The easiest way to do this is just to look up in your favorite integral table that x squared e to the x squared, e to the minus x squared equals square root of pi over 2. So this is the Gaussian integrals. You're allowed to look those up. That's fair. So you either integrate this by parts or just look up this answer and then do a substitution, and you get 2 dt. And then for sketching, I don't have you guys sketch nearly enough. I feel like sketching is really valuable. I'm on the qual committee, and one of my collaborators on the thermo qual really likes putting problems where you sketch stuff. I should take a hint from his book. So anyway, so what does this look like? So your sketch should look like, here's my rod. My temperature is going to start off like a very narrow Gaussian. A very narrow Gaussian is also a delta function, but immediately it becomes a Gaussian and not a delta function anymore. And then at later time, you get a wider, lower Gaussian. And then at late time, you get a yet wider Gaussian. So things just expand, and the width of the Gaussian, it goes like x squared, so the width of the Gaussian gets linear with time. And I can write up a full solution if anybody's really interested. That's just what it says here. I don't know if I'm actually going to do that. Go over there. Okay, derive an expression for the convective derivative of four vorticities. So one of the potholes with doing physics is getting the terminology right and understanding what terminology is meant by what. And so this is something that I haven't really beaten you guys on the head with, but the convective derivative, or the material derivative, or the Lagrangian derivative, not the Lagrangian, but the Lagrangian derivative, and the convective derivative. Did anybody else come up with any other names for this while they were in searching? So there's several names for this thing. And sometimes we'll write it as big D by dt. All of it is just the full derivative, d by dt. But because it touches so many different fields in so many different ways, so d by dt equals partial t plus v dot rad. Because it has this weird flavor, and because it shows up in so many places, a lot of people have named it a lot of different things, and it's connected to so many different things. So Lagrangian means it follows the mass. So this is the derivative that follows the mass, whereas the Eulerian derivative is just this part, and it's fixed with space. So the difference is whether or not you're fixed with the fluid or whether you're fixed in space. And that's the left-hand side, or just this part on the right-hand side. And sometimes they use capital D to denote this derivative because, as is evidenced by this right here, it is easy to screw up whether you have a partial or a full derivative, especially if you're handwriting. This should be a partial derivative and not a full derivative. Hopefully that didn't catch anybody, but that's me being sloppy. So people will use capital D to denote this full derivative because you can't screw up the velocity part. Okay. So what we want is an expression for vorticity. Hang on a second. Just because the flow sucks if I screw up the vector identity. So we start off with d by dt of omega equals del cross v cross omega. So this is something you look up in the book. If you started from the velocity equation, then hopefully you got here. So what we want is d by dt of omega. So what I'm asking you for is d by dt of omega, which is partial t of omega plus v dot grad omega. So whenever I ask you to find something, the best thing to do is start off with that something. So this is that something. This is the thing that's complicated. This is already written down. So this is v cross grad omega. So if we expand this with our favorite vector identity is del cross A cross B equals A div B minus B div A plus B dot grad A minus A dot grad B. So if I'm going to plug this in for V and omega, div V is 0 because we're usually assuming incompressible. So that first term goes away. Div omega is 0 because it's the curl of a field. So its divergence is 0. So the first two terms are 0. And we're just left with B dot grad A, which is omega dot grad V minus B dot grad omega. So when I plug that into here, then d by dt of omega equals omega dot grad V minus V dot grad omega plus V dot grad omega. And those guys cancel out. And you're left with the full derivative of omega is omega dot grad V. Did anybody have any troubles doing that? Or questions that they had along the way in that derivation? Yeah.
I just like, how do you interpret like some vector dot grad like mathematically?
That's the next question. Did anybody have any questions about this part? Everybody's good on that? Sweet. So now I'm going to get to that question. So my question for you is, Brahm's question, how do I interpret this term? What does this mean? What's in it? So what does a dot product mean? Everybody knows that.
The divergence?
No, just the dot product, A dot B. What is a dot product mean?
It's the
Projection, right? Dot product means projection. So I have omega dot grad as my operator that I'm looking at. And let me turn the camera on the right thing. So omega dot grad is the operator that I'm worried about. I do not need to be carrying this book around anymore. I got what I needed. I think I need to get this vector identity tattooed on my arm or something.
Literally. I need all of them. Every single one.
So this is a projection, and you can't, grad is a verb. You can't really project onto a verb, but you can project the verb onto omega, right? So I have, omega is some vector field, so here is a bit of omega. It has some shape, it has some direction, it has some connectivity. So, you know, the length of this is dictated by turbulence. How many of these I have is dictated by turbulence. The morphology of all the omegas, little bits of omega kicking around, is all determined by the turbulence, but that doesn't matter. I have some vector field. And so I'm going to project, so I have my vector field omega, and it's got lots of properties. And then I have my vector field V. Even orange, which is some other vector field. And it's actually like, it's complicated, right? So we're taking grad and we're going to dot it into omega. So that means we're going to project the gradient operator on the vector field omega. That means I'm just thinking about, so I'm going to pick 2 points in space. So remember what a derivative means. D by dx of f is f at x plus dx minus f of x over dx, and dx goes to 0, but whatever. You can do so much without taking dx to 0. It just, some things bite you in the butt. But this is a derivative, right? It's just the difference between 2 points in space, right? So what omega dot grad means is I'm projecting my derivative along omega. So I'm thinking about a point here, and then a point that's up omega by a little bit. So it's just like taking the universe and rotating it so that omega is horizontal, and I'm just taking the x derivative. So it's just the derivative along omega. Does that make sense? More or less, yes or no? Not a little bit?
You
Maybe.
mean the derivative of v?
It's the derivative of v along omega. Now I could put anything I want in here. This is going to be the derivative of v, and it's going to be the derivative of, so this is a vector. So omega I and vi, so this is a vector, and the vectorness comes from the fact that this is a v. So I've got one derivative that's acting on 3 vector components. Does that make sense? And the vector derivative is along omega. So now, the question is, what do we typically expect the sign of this to be? So I have 2 points in space, 1 point here and 1 point here. Let's up a little bit. So now we can flatten it, right? How many ways are these 2 points going to be moving apart versus how many ways are they going to be moving together? Think about that for a second. Draw a bunch of diagrams, draw a bunch of vectors in your head. Is it more likely that they're moving away from each other? Or is it more likely that they're moving towards each other? Well, there's more ways. This one, all of this space, all the vectors in this space, and all the vectors in this space are all moving apart. The only ways that you're going to move things together is in a small solid angle. So the ways to move apart is much larger than the ways to move together. Does that make sense? So this is going to, in general, be a positive quantity. Does that make sense? So d omega dt tends to go up. That makes sense? So let's back up a second. So interpreting this is a little tricky, but let's go back and talk about it again. So I've got this vorticity, and I'm thinking about the velocity along my little vortex tube. A vortex tube is like just a swirl in water. So if you remember from the first day, we had that ring of bubble, and then the little jellyfish gets sucked under the ring and gets sucked up. That is a little loop of vorticity. So they're not always in loops. Usually it's in weird, long, complicated lines. So so in general, one of those lines is going to get stretched out. And as it gets stretched out, then omega increases because d omega dt is this positive quantity. Additionally, you can think about this in terms of, so why does it get smaller? So it gets smaller because A times omega is constant, where A is the area. Why can I say this? Whose theorem says this?
Kelvin.
This is Kelvin's vorticity theorem. So this says that the vorticity over an area is constant. So if omega goes up, then the area has to go down. So my length goes down, so my thing gets smaller as it starts to spin up. And you can think about this as just a conservation of angular momentum. Just like when you're sitting on the chair, when you're in freshman physics and you pull your arms in, you go spin up. It's the same physics. I do that at my kids' school for science night, and I just spin kids around on a stool for 3 hours.
And they love it.
They love it. It's the most entertaining thing. It's also hilarious when they fall off, but I try to not do that too often. Okay, so anybody have any more questions about that question? Does everybody feel at least somewhat comfortable with the vector derivatives, or do you want me to talk more about it? Or do you want me to talk more about it in like 10 minutes, once you've digested for a second? That I'll probably do. Okay. What is next?
Professor,
Yeah.
just to clarify, so it's the projection of how much velocity is changing
Yeah, it's how much velocity is changing in the direction of omega.
in the direction. Okay.
Where's my thing? There you are. All right. Derive the Reynolds stress. Did anybody have too much trouble doing this one? No? Yes? It was relatively painless? So it's not, it's a little bit of algebra, but it's not really too bad. So I'll outline it. I'm not going to walk you through every component. But so you start off with saying that the velocity equals some mean velocity plus a fluctuating velocity, which is exactly what we did when we derived sound waves, except now we can't throw this one out. So we start with the momentum equation, d by dt of v equal plus div vv equals whatever, other stuff that I don't care about right now, because the other stuff is well behaved, because all the other terms are linear, so they're all well behaved. The only poorly behaved term is this term. So we plug in and then expand. So we get d by dt of v bar plus v prime plus div, we get a v bar plus v bar v prime plus v prime v bar plus v prime v prime equals the other stuff that's well behaved. And then we average over everything, and then we look at what dies. So this term dies, this term stays, this term dies, this term dies, this term stays, and this is the term, when I average that, that doesn't go away and makes now my Reynolds average Navier-Stokes equation looks different than the Navier-Stokes equation. Navier-Stokes says d by dt of v plus div v plus nu div v. Navier-Stokes says this equals 1 over rho grad p. But the Reynolds average Navier-Stokes says d by dt of v bar plus div v bar plus v prime bar equals minus 1 over rho grad p. And this term is the Reynolds stress. And what does it represent?
It's how,
Yeah. Look up.
it's how much the fluids next to each other push on each other.
Which part? Which component of the fluid? This part or this part?
The fluctuation.
Yeah, it's the fluctuations interacting with the fluctuations. So it's little bits interacting with little bits. The little bits. So this term here is velocity, mean velocity pushing the fluctuations around, and that just washes out. And this term is little fluctuations trying to push the mean velocity around, and those average out. But the interactions of the little fluctuations with the little fluctuations don't average out, and they combine to give you some macroscopic properties in all kinds of intriguing ways. Okay. Okay, turbulent cascade. Let us qualitatively discuss the turbulent cascade. So if I stir a pot of water on, so say I've got one of those immersion blenders, like a handheld blender that's like this big around, and I stick it in a pot. Does the energy cascade to smaller scales or bigger scales? Smaller scales. Now this changes if you're looking at. Here I'm going to go on a tangent for a second because that's not always the case. If you're in 2D, if I'm in 2 dimensions, then how many components of the angular momentum exist in 2 dimensions?
2.
Only 1. Because I can move around this way in my plane, so this is a plane. I can move around this way in the plane, but I can't move around this way. So there's only 1 component of angular momentum that matters. So angular momentum in 2 dimensions becomes a conserved quantity. And just the z component of the angular momentum is a conserved quantity. Angular momentum is already conserved. So that makes weird things happen. So if you ever watch videos of 2D turbulence, or if you watch atmospheric fluid dynamics is kind of quasi 2-dimensional, especially if you're in the Great Plains in the Midwest, where nothing happens for 1,000 miles, and the ground is perfectly flat except for an ever so slight tilt to the east, so the air just kind of drifts in that direction. But then you have these little bits of vorticity, and it's conserved. So if I have 2 positive bits of vorticity, they merge and they get bigger. If I have 2 negative bits of vorticity, they merge and get bigger. So in 2 dimensions, the vorticity actually cascades to bigger and bigger scales, which then results in things like hurricanes and tornadoes. There's a lot more that goes into a hurricane and a tornado than just the energy cascade. But if we were in a fully 3-dimensional system, you wouldn't make a hurricane. It's the fact that it's a 2-dimensional rotating system that makes the hurricane. And that hurricane angular momentum is not going anywhere because it's conserved, because that's the only component that exists, is the horizontal component. So in 3-dimensional turbulence, the cascade goes to smaller scales. So there are 3 regimes that I've talked about in the turbulent cascade. Somebody yell out the biggest one.
Injection.
So you got the injection scale.
Oh, okay.
Right.
I understand what you meant by biggest.
Yeah, no worries. So the physically largest scale is the injection scale, and that's where you're dumping the energy in. And bigger than that, you may have plenty of system, and you may leak a little bit into bigger than that, but because if you actually take something that's spinning and stick it in your pot, you'll have a net rotation. So you can couple to larger scales, but not very well. And then what happens at smaller scales? What do we call that space?
Diffusion.
The inertial range.
Oh,
And what's the dominant physics in the inertial range?
Cascade.
Yeah, the cascade. If I look at Navier-Stokes, d by dt plus v dot grad v equals -1 over rho grad p plus nu del squared v. The really interesting bits are this bit or this bit. Which one's dominant in the cascade?
Oh,
The first bit. So this is velocity pushing velocity around. So this is, I have some swirl and it gets jacked up by some other swirl and about the time it takes to turn around. And then what's the smallest process?
Diffusion.
So that's diffusion. So that's the molecular diffusion at the bottom of the cascade. So there's dissipation. And dissipation isn't only done by molecular diffusion. Ultimately, it's done by molecular diffusion. But the structures get weird and complicated, and I'm not going to get into those details. But the diffusion process. Okay. Sketch the behavior as energy as a function of L. When I ask this question, I haven't graded this yet, but when I ask this question, you got to pay careful attention about whether I ask you to sketch it with respect to L or K. How are those 2 graphs going to be similar to each other. They're going to be flipped, so don't draw the backwards. So as a function of L, L, so I have big scales over here, so I start off with big scales, and then I have a power law, so this is now log of L and log of V squared. I have a power law and then some dissipation scale here. So I have my injection scale, my inertial range, and my dissipation scale. It should go like that as a function of length scale. Yeah, and when you're making a graph, the dominant axis increases to the right everywhere, unless you're being a dumb astronomer and you have to make your things go backwards because we got stuck on something 2,000 years ago and haven't been able to shake it. That's another tirade about why astronomy is dumb. Yeah?
So I understand why the graph is supposed to look like that, but finding the equation for like relating K to L in the different regimes, I can't understand that.
Yeah.
Like all I got was in the book is K is approximately equal to 1 for L, so I did that, but I don't understand how that changes in each regime.
Yeah, okay, so the only place where you can derive anything with L is in the middle.
Okay.
So that's the only place that you derive stuff, because the outer scale is a boundary condition, and all I can say here right now, a priori, before seeing the actual experiment, is that there's going to be some large scale. And you can't really derive anything about that. Because that's going to be, it's coming from a storm in the South Pacific that is 50 miles across, or it's coming from a jet that is shooting gas into the interstellar medium at some rate. So the details about this, you can't really say anything other than it's large scale. And then at the small scale, you really can't say anything else because it becomes a fractal in really complicated and weird ways, and it's probably not even just one fractal. There's probably a couple competing fractal processes going on down here that we're not going to get into. So, and there's nothing that you can really derive analytically about those processes either, because you can wave your hands, but down here we just say it just gets taken care of by the del squared V term, and we'll leave it at that for now. And then the inferior term, this is where you can actually say something. And what you can say, and this is the chain of logical thoughts that Kolmogorov went through, and also the ones that everybody else goes through now. So the first thought is that the energy injection rate equals the energy dissipation rate equals the energy rate as a function of scale. So I've got some energy that I'm dumping in at some injection scale, E in, and that's getting dissipated because it's a steady state. Now, okay, what happens when it's not in a steady state? You have research papers about that. So the transition to turbulence, and when turbulence turns on, how do things become turbulent? When is it turbulent? All very interesting and very complicated questions. We're just going to start with it is steady state. So everything I'm dumping in gets dissipated. And the fluid sets up exactly what kind of dissipation structures it needs to generate for the injection that I'm putting in. So these two are equal based on, first, the assumption that it's steady state, which is a fine assumption. I can totally make a state like this. And then second, what's the real physics is magic, near as I could tell. Why do I say that? Because, okay, so I'm going to go off on a tangent for a second. So I had showed you that the dissipation scale equals the length scale times the Reynolds number to the -3/4. So what this equation says is that the size of the structures at the tiny scale depends on the Reynolds number of the flow. And the Reynolds number of the flow is set at the large scale. So there's this fascinating and not well understood connection between how things actually dissipate, what are the sizes, what's the size spectrum of things that are actually doing the dissipation, and the Reynolds number. So anyway, so there's a lot of magic in this assumption, but we can just say steady state, close enough, yeah.
So I just, like, the book said all of this in
Yeah.
like 1 or 2 pages.
Yeah.
So I just wanna make sure, like, some of them, for some ranges, is the Reynolds number like really big or really small or close to 1? Like, I was a
Yeah.
little confused about that, yeah.
Perfect. So, where is the Reynolds? So Reynolds number is a funny thing. So Reynolds number is what? LV over nu. Nu doesn't change. That's the same everywhere. But L and V, like the Reynolds number has a length and a velocity associated with it. So I'm going to talk about, generally if you talk about the Reynolds number, you mean the integral scale of the outer scale of the driving and the outer velocity scale. But if I'm just looking at a little patch of fluid, I can talk about a Reynolds number there too. So the little local Reynolds number is going to be huge over here and slowly decay so that down here it's around 1. So where it starts to dissipate, it's around 1. Because remember, the Reynolds number is the battle between this term and this term. So this term is on top and this term is on bottom. So when the Reynolds number is near 1, then this term is starting to become very important. But when the Reynolds number is very large, then this is the term that's important. And that's the only thing we have to worry about. Does that make sense so far? Because there's several. So this is it's a very easy derivation mathematically. It's not an easy derivation conceptually because you've got to put these pieces together. So the first thing, well, let me step back, forget all my random asides. So the first thing is that the energy injection rate and the dissipation rate and the rate that it flows through the cascade are all the same. That's assumption 1. 2, so that means that the energy rate has got to be the energy. So if I want some kind of rate, Q dot, that's equal to the total quantity over some time. That's it, right? Now, you could finesse that a little bit and make a limit, but Q dot is just some Q over time. So epsilon, this is an energy dot, but we just call it epsilon. It's got to be the energy over the time scale. So now here the arguments that you need to make are that the energy is just V squared. Rho is just a number, right? Because density is constant, so we're doing everything per unit mass, which is fine because density is constant. So the energy is V squared, and the time scale for a thing like this to shred all its energy is about the time that it takes for the flow to cross that structure. So the time scale is equal to L over V. Does that make sense? So then we get the time scale is L over V, which is just equal to V cubed over L. And then you're basically done with all of the arguing and whatnot. So now we can say that epsilon equals V cubed over L, which then turns into V equals some number times epsilon to the 1/3 times L to the 1/3, or V squared equals some number times epsilon to the 2/3 L to the 2/3. That number's square thing. Okay, does that all make sense? So the important bits are, you've got to assume that we're in steady state. You assume that the energy injection rate is the same as the transfer rate, is the same as the dissipation rate. Then you assume that the time scale for an eddy to get shredded is just its crossing time. And that's the dodgiest of assumptions, but it seems to work out pretty well. And then you're left with this. And then if you want the K, then you take a Fourier transform, and L goes to 1 over K. But when you do that Fourier transform, you also pick up a K. The Fourier transform of a power law is a power law plus 1 from the integral. But I like leaving it as a function of length because I feel like this is more instructive. In the literature, everybody does everything as a function of K because Fourier transforms are great. But I like leaving it as a function of length because I feel like you're much more connected to the assumptions that you had to make going into it. Okay. Okay, so that's number 6. So I just talked an enormous amount. You can distill that and say all that in a more compact fashion. But think about that, yeah.
So the only place we can actually like analytically say something about the energy versus the length is with that 5/3 law.
Or this 2/3 of L.
Okay, which is arguably the same thing. It's just Fourier.
It's definitely the same thing.
It's just the Fourier transform is the only thing.
That's right. The only difference is the Fourier transform.
Gotcha.
One is I'm doing it in spectral space, and one I'm doing it in real space.
Gotcha.
And I can go between the two easily. But this is only true kind of in here, in the inertial range. Because when I'm in the outer scale, then I have this big plus F, which is my extra forcing, and the F is the dominant term in the outer scale. And down here, it's the interplay between these two terms, which is even worse than just having just this one, because this one doesn't go away. Okay, any other questions about inertial subrange and all of that? Are we reasonably okay? How are we on time? That is fascinating. Okay, now I'll show that in the inertial range, two particles will separate like t cubed. So for this one, I had to stare at this one like 11 times before this derivation made sense to me. So we have that V goes like L to the 1/3. So dl dt is L to the 1/3. Now I want dl squared dt, so I just multiply by L equals L to the 4/3. And I get a 1/2 because I integrated by parts, but then that 1/2 goes into the waving my hands, so I'm just going to wave my hands right for that. So then you solve this differential equation, and you find that L squared goes like T cubed. Setting it up is easy. Solving it is straightforward. I just put the T over here, put the L over here. L squared is my quantity. So this is L squared to the 1/3. And you've got to do that integral, and then you're left with L squared goes like T cubed. Does this make sense to everybody? Yeah.
Is there a reason you can't just keep the just normal dl dt and multiply by L to the -1/3 on each side, and then integrate from there? Because that got me the same thing without doing the dl.
Why? So I multiply L to the -1/3 times dl dt equals 1.
And then
Yeah, and
times
you bring the
dt on both
dt over,
sides.
and then you integrate.
Do you get here?
Yeah.
Cool.
Right?
There's many paths up that hill. Yeah, that works fine. I think doing it this way feels more intuitive to me, but whatever makes the most sense. As long as you start here and get here, and don't jack up the math too bad. I mean, you really have to get here because that's the solution to that equation.
Yeah.
So yeah, that's fine. Yeah, I can't do that in my head while people are looking at me. I had, when I took E&M, my professor, he was just a fantastic professor. I got an enormous amount out of it, but he said several times after he would fuck up a derivation, he was like, it's hard to do algebra at the board.
It is.
I'm like, man, I didn't really understand it at the time, but now that I do it. Okay, so I throw 2 bottles in the ocean with messages in them. How does their relative velocity evolve with their separation? So okay, assume that the correlation length is 5 kilometers and they begin 1 meter apart. So where do they start in this? Do they start in dissipation or inertial or driving scale? Well, the inertial, the correlation length is 5 kilometers. So things are being driven on at least 5 kilometer size scale. So it's smaller than the driving scale. What about the dissipation scale, which we've been saying so far is molecular? Are these molecular close together? No. So where do they start? They start off in the inertial range. So how does their velocity change as they get further apart? Does it increase or decrease or stay the same? It increases, not quite linearly, it increases like L to the 1/3. So as they get further apart, they get the velocity gets larger. Cool. Any other questions about anything?
Do you explain why that would happen?
Which?
Like, if they're going apart, if velocities increase, like if you're just...
Yeah. This here. So this comes from all of this other crap that we described. Is we described trying to talk about how does velocity have to change with time, and what we talked about was just a time derivative, but that gets us the spatial distribution of how velocity changes. So if I take 2 points, their velocity is going to be kind of like 1/3 of the distance apart. So if I take 2 further apart points, the velocity is much bigger. The way to think about this, so there's, oh, hang on a sec, let me, it always goes poorly when I have a dumb idea and okay, so there's this poem. Okay, big fleas have little fleas upon their backs to bite them, and little fleas have lesser fleas, and so on ad infinitum. Is a poem.
I saw that,
Yeah.
and I was like, this is for physicists only.
Yeah,
Like,
right.
This is not beautiful.
Is it in the book?
No, I went through, when I was like, you know, because the book is like really short about this inertial range and stuff like that, I went on like several websites,
Uh-huh.
and on Wikipedia they have a
Oh yeah. Okay. So this poem. So it goes somewhere. So the idea is basically, if I have a dog, it's got parasites on it. They're small. If I have a flea, that's the parasite. It also has parasites. So fleas have parasites, and they're smaller. Those things probably also have parasites, which are even smaller than that. So Richardson famously tweaked this to say, big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So the idea, and I'm coming back to Abraham's question, which is why this? And I did some math to show why this, but that's not necessarily. So, oh, actually, this Da Vinci has this incredible graphic. Oh, come on, give me the picture, stupid thing. Well, we'll just
helicopter.
No.
No.
It's. Okay, I'm going to turn the light off real quick. So this image is Da Vinci's understanding of turbulence. It shows up a lot because one of the things that it really captures really nicely is that you have these big whirls, and then on these big whirls you have littler whirls, and on those littler whirls you have littler whirls, and on those littler whirls you have littler whirls, and it's not quantized in an integer fashion the way harmonic oscillators are. It's quantized in a fractal fashion, so it's a huge hassle for us to understand. But basically you have large scale motions, and then you have, on top of those large scale motions, you have motions that are somewhat smaller than that. And then you have motions that are smaller than that and of smaller velocity, and smaller skies and smaller velocity. So you get this fragmentation of tiny, tiny, tiny whirls cascading down from this big whirl. So if I have two little swirly bits down here, they're going to have some relative velocity. But when they get drifted apart, then as they're on as they get larger, then they're on some larger whirl, and that larger whirl has a bigger velocity. It's going to carry them a little faster. And then once they get a little bit further apart, then they'll be on a bigger whirl, and that bigger whirl is even faster, and will take them apart even further. And then they get on a bigger whirl, and it just keeps going up and up and up and up, and things get carried apart very quickly. So this is why it's much more efficient to stir your coffee than it is to just wait for the milk to diffuse through your coffee, because that will take many days versus 1 second. Okay, is everybody reasonably good on all of this? Homeworks?
So this is kind of related to the whole fractal thing where you can zoom into a structure and it's the same structure ad infinitum.
Yeah, that's accurate. So, so all of this is a fractal. And so if I take any part of it, I'm going to get a structure, a set of structures, an ensemble of structures. If I look at a bigger space, I'm going to get the same ensemble of structures. And the reason for that is because everything at the end of the day is a fractal when you get down to this level. Nature loves making fractals. Okay. So now I'm going to how much time do I have? No idea if that's correct.
37.
Oh, it actually is correct. All right. Okay, so now I'm just going to go through everything. Let's do everything. What would you guys like to talk about overviewing or reviewing for the midterm? I've got a list of things that I think I talked about, and I'm going to go through that and use that as a jumping off point for you guys to ask questions. But if you have other questions that you want to see, if one of your questions is, can we go over turbulence again, I'll do that at the end again, just that you've had 10 minutes to marinate. But let's talk about other stuff and things that I like. So, my chocolate doesn't, so. Continuity, Euler. Make sure you can derive these like cold. Like you just gotta show up in front of your mom and her bridge club. And they're all pharmacists, so they're all bright, but they don't know fluid dynamics. How do you explain fluid dynamics to your pharmacist mother or whatever? You know, pick somebody who's intelligent enough, but doesn't know this stuff. Make sure you can do these derivations for them, except for the calculus bits. Navier-Stokes adds viscosity. So what do we want you to know about that? So all kinds of things. So for this test, I'm not going to ask you to derive the viscosity, but I might for the final. High likelihood that I'll ask you to derive one or both of these for the midterm, because I think this is one of I think the key beauties of this field is you can easily write down the constituent equations, which is really hard in quantum mechanics or E&M. Like you can derive Maxwell's equations by taking the minimum of a relativistic action. But that's not how they did it. It's not how you do it. It's just how you can see that it has to be true. But continuity in Euler, you can just say mass is conserved, and therefore this has to be the answer. And Euler is similar mass is, or F equals ma, so in a continuum setting, we're just reinterpreting F equals ma in this continuous mechanics setting. So that gets you the convective derivative, and it gets you the pressure term. The pressure term I'm not as super worried about, because that's easy. The convective derivative is the one that you should have your head around. I think everybody does. I don't think anybody's had any trouble with that. But make sure you can do those things. But one of the beauties of this field is I can start off with things that I can just write down, and then I can see the edge of human understanding, which is like really the end of the human understanding are these fractal structures that build up in the dissipation scale. So we don't understand what's going on there or why it's happening. We know it's not. We know that it's complicated. Okay, Navier-Stokes. So what is nu? Think about what nu is, and remember that nu is approximately order of magnitude, ballpark-ish. That chair's gonna kill me. Maybe I'll leave it. The mean free path times the thermal speed. I'm not going to go. So also keep mean free path and thermal speed in mind. So think about what those are. I can go through all of this stuff, but I'm not going to go too deep down anything right now. Then we talked about, vorticity. It has some equations. It's conserved in a funny way. I'm not going to ask you for Kelvin's vorticity theorem on this midterm, but I might on the final. Now, okay, I'm going to say I might on the final do a couple of very long derivations. They're not all going to be on the final, but there are some that I might. So while you're deriving or while you're studying, make sure you at least have your head around how this derivation works. Not strong enough to reproduce it, but so that you've seen it, so that you're stronger. And we didn't talk about vorticity production very much. We talked about linearization things. Oh, hey, a robot is trying to distract me. Then we talked about linearization. And how to take a horrible set of equations and turn them into a set of equations that you can solve. So you first start off with a background, Q naught, and then you perturb Q naught plus Q1, and then you Q1 squared equals 0, so you throw out the multiple, the higher order terms, and then you do some Fourier. And you get out of that, for us, you get a V phase, which is omega over k, and a V group, which is d omega dk. And the phase speed is the velocity of one front of a wave, and the group speed is the velocity of the packet. We talked about linearization for several things. We did it for Euler to get sound waves. We did it with Euler with a boundary condition to get deep water waves and shallow water waves. Yeah, so there will probably be some kind of linearization of something vaguely related to what we're doing, just because I think it's important to put your hands on it.
Professor?
Yeah.
You said group velocity is dv?
Yeah, d omega dt.
D omega.
D omega dk. We talked about shocks. So most of the stuff that we did at the beginning, we could assume that things are incompressible. For a little bit in the middle, we could not assume that things were incompressible. So what did we do? So we had shocks. We did method of characteristics to show shock steepening, to see how shocks can get sharper as the flow goes on. We did the Rankine-Hugonio relations, which show when you have a shock and you're moving along with the shock. Might have you do some method of characteristics, might look at it. Very likely you'll see Rankine-Hugonio relations. So making sure you understand where those come from. We talked about de Laval nozzles. And I need to beef up the homework problems on the de Laval nozzle. So the Laval nozzle is this converging, diverging nozzle where when it's converging, it accelerates until the sonic point, and then as it's diverging, because it's supersonic, it accelerates again, which is the coolest thing, right? That it works. My collaborator sent me an image of, oh, maybe, do I have, no, it's on my computer upstairs. Sent me an image of our plate of nozzles. So I've got this project that I'm doing with a guy in mechanical engineering, and we're gonna take a whole bunch of these nozzles, like 60 of them, and put them all right next to each other. So we have this huge wall, okay, it's about this big, but this huge wall of supersonic flows that are all getting born right next to each other, and hopefully they'll interact and become turbulent. It's gonna be so cool. When, before the end of the semester, I should have data to show you guys. So there probably isn't gonna be very much on those nozzles because I didn't cook up any good questions. We talked about Berger's equations and the set-off. Berger's. We talked about the set-off last wave. And this is just dimensional analysis. So there very well may be some dimensional analysis. I like waving my hands. Dimensional analysis is the first step in waving your hands. That's what your wing looks like. Yeah, so these are the techniques that we have to deal with compressible flow and supersonic flow. So then we talked about stability. So stability is a lot like the linearization we did, except that now sometimes your frequency is in the complex plane. So if your frequency is complex, then some of it blows up because of e to the I omega turns into the e to the, just e to the gamma t. So we talked about a couple of things. We talked about helioseismology. We talked about two-fluid stability. And so those were, I'll write this over here. Kelvin-Helmholtz, which is a shear instability, and it makes these whirls like this. And Rayleigh-Taylor, and that's heavy on light, and that gives you bubbles and spikes. And we talked about genes, which is the gravity instability. And so you should know about the gene's length and the gene's mass. We talked about convection and the Schwarzschild that's a D. The Schwarzschild criteria, which is when do you start to boil? When the density goes down, when you go up. Yeah, and then we talked about turbulence. Which is really what we started with, but what are the things that I might ask you about turbulence? So be able to describe the cascade, what scales are important when, what pieces of Navier-Stokes are important at which part of the cascade. The v to the 1/3 law. Make sure you can derive that and understand what it means. What are the other things we said? Just diffusion. In the various regimes, so diffusion happens in a couple of different ways in a couple of different regimes. And we talked about the Reynolds stress.
So,
V prime, V prime, bar.
so there's molecular diffusion, and what's the other one called?
Turbulent diffusion.
Turbulent.
And we talked about two different kinds of turbulent diffusion. So one turbulent diffusion is at the bottom of the cascade, not quite to the molecular diffusion level, but not actually in the cascade. In that transition region, then things move basically together ballistically. So that's one of the diffusions that the book does. The other diffusion the book does is when you're much larger than the correlation scale, and then things again are diffusive, where x squared goes like t, but then in the intermediate range, x squared goes like t cubed. So, yeah, so in diffusion, going from smallest to biggest, you get molecular. Chocolate gato. Ballistic. Richards, which is the inertial range. And then again, turbulent diffusion when you're bigger than the driving scale or the correlation line.
Dr. Collins?
Yeah.
What does that say under De Laval?
What?
Under De Laval. What
De Laval Burger's. So Burger's equation is Euler's equation without the pressure. And this is, Burger's is easy to make blow up real easy. So that's the reason we went through that, is because it doesn't have anything to prevent it from blowing up. And then Sedov is the point source explosion. So you drop a bunch of energy E into a point, and then you use the basic assumptions. So the assumptions that go into Sedov Taylor blast wave is that only the density matters, and the energy and time. And that gives you some size scale. So those things are related by dimensional units, and so you get the size versus time just by dimensions. So that's very cool.
Dr. Collins?
Yeah.
So each of those diffusions have a x squared goes like t to the something.
Yeah. So x squared goes like t, x squared goes like t squared, x squared goes like t cubed, and then x squared goes like t again. And there's not a smooth transit, like there's some smooth transition between these things. It doesn't, there's not like a step. It won't feel a bumpy ride as it does as you go through these different regimes. Yeah. So anything else? Is there anything else that you think we talked about? This is what I think we talked about. Oh, I got a couple minutes early. So, does anybody have any other questions on anything? That's, yeah.
I guess like what would we be looking at for helioseismology? Because we really talked about it.
That's a very good question. So, well, we talked about helioseismology. The one thing that we did do actually does make a good test problem. So the one bit, it's the very end, and basically you start off with dv dt is gm over r squared. And then you say that at some r naught you have a stable solution. And then you perturb that, R naught plus delta R, and then your rho goes to rho of R naught plus delta R cubed, rho naught. And then you do Taylor expansion on that. And then you get the same for the pressure. And then you get a bit about the stability of the star, where it turns out that gamma has got to be bigger than 4/3 for the star to be stable. Remember going through that? It's a nice problem. It's a little long for the midterm, but if that's what I'm feeling, that's a problem that might show up. So go through that. It's not super complicated. It's just write down F equals ma, perturb it with this, R plus dr, and then do a couple Taylor expansions, and then simplify. And then you get this equation here, that gamma's got to be bigger than 4/3. So if gamma is less than 4/3, then when I squish it, it collapses. Or if I stretch it, it blows up. Because the gas is too squishy. But if it's bigger than 4/3, then it's stable. And when you squeeze on it, the pressure will go up enough. Yeah. Any other questions? Everybody feeling pretty good? Yeah.
How many problems are?
I don't know. I haven't written it yet. That's what I'm going to do. So today, I'm going to grade homework 4. That's the very first thing I'm going to do when I get back upstairs. And then I'll write the midterm. But I haven't done that yet. So I got a pretty good idea about how long you guys take. So probably like 4 questions, maybe 5, unless they're short. Maybe 6 if they're all kind of easy. Maybe 4 if they all have some teeth. Probably not as few as 1 or 2, because then then there's no margin for you guys stubbing your toe on the problem. So I like to have several problems. Some are slow pitches and some are harder. So I like to make sure that I pad it so that if you're having an off day, you're not totally hosed. So probably 4, maybe 6, somewhere in there. Yeah.
So unlike all of the other readings for chapters 4 and 5, it never says, what are we allowed to skip? So are we just allowed to, can we just assume that everything that's on this board is pretty much exactly what's going to be, like everything that's going to be on the test appears on this board somewhere? Is that a good assumption?
Yeah. I mean, so I don't, especially for this class, I don't believe in pulling stunts out of thin air or making really hard problems. So if you've done the homework and you've gone through all of the readings, convolved with the stuff that I actually talk about, but I do talk about most of the things that are in the reading. If there's something in the reading that I didn't talk about, like there was a bit about lift on a wing, I never talked about that. If it wasn't on the homework, it's not going to show up on the test. So for the most part, these are the things that are going to be there.
So we can skip some stuff like stream functions or
stream functions I didn't talk about, but potential flow I did. So make sure that you understand how potential flow works. So did you have other things you wanted to ask?
No, I was just, because there were, when you assigned readings for chapters 4 and 5, there was no indication to skip anything, like there was in some of
the other ones. Yeah, in 4 and 5, let's see, let me just pull it up. I have the book right here. What's in 4 and 5 that I didn't go over? So in 4, yeah, so I'm not going to ask you, in section 4, I'm not going to ask you for the flow past a cylinder or the stream functions, the last 2 sections. I'm glad that you read them. They're important to have read, but I'm not going to assign any problems. And in 5, the last 2 sections, I won't, aerodynamic lift and accretion disks and astrophysics, I'm not going to ask about anything in that. But then in 6, basically everything in 6, and basically everything in 7. I won't ask you to do the two fluid instability derivation on the test, just because, that derivation by itself will take you, if you know what you're doing and you're quick about it, it'll take you 20 minutes. So I won't ask that, but I might say something about Kelvin-Helmholtz, and you should know what that means. That means that you have velocity, or Rayleigh-Taylor means that density is heavy on top. So understand what the things are. Yeah, 7 I'll do everything. And 8, everything in 8 is fair game, but 8, as you've noticed, the stuff that I spend all my time on is half a page, maybe a page in that section. And then the rest of the stuff is all the other stuff that you have to talk about turbulence. So, so in turbulence, watch my lectures and go through those and listen to the stuff that I talked about most. I mean, read the book, but the book does it in kind of in a different way. The turbulence section is where I deviate the most from the book, because it's what I do for a living. So, and the book is 25 years old. So, although most of the turbulence stuff that we talked about today is all from the 40s, so it's all old stuff. But anyway, so I think that's it. I think that's it. That's a good question. Any other questions on stuff I might include and stuff I might not? All right. Have a good day. Oh, do you want office hours tomorrow? I mean, do you think you'll show up?
I usually have a work night, so.
Is there a time when you want? I'll tell you what, if you want to meet at some point in time tomorrow, I'm around all day. Shoot me an email, and you can probably just show up, but a lot of times I'm in a meeting or whatever, so shoot me an email. If you want to meet, I'm around all day. If you want to meet, just shoot me an email. All right. How you doing?
The pie drive cube is running there.
Oh, good.